Okay, Section 6 of Chapter 2, Logarithmic Functions. Objectives. First objective, the student will be able to use and apply inverse functions. Second objective will have to do with logarithmic functions. The second objective is that the student will be able to use and apply logarithmic functions and properties of logarithmic functions. There will also be the sub-objective. The student will be able to evaluate logarithms. The third objective, the student will be able to solve applications involving logarithms. So in this video, we're just going to deal with the objective. The student will be able to use and apply inverse functions. In this section, another type of function will be studied called the logarithmic function. There is a close connection between a logarithmic function and an exponential function. We will see that the logarithmic function and the exponential functions are inverse functions. We will study the concept of inverse function as a prerequisite for our study of logarithmic functions. So what is it that inverses do? Well, if you have a pair of inverses, what they do is they undo each other. So let's say you had an input element, an x value. You had an x value, and you're going to run that thing through a function f. Well, f maybe has an inverse. And so you're going to make that f of x now the input of a new function, which is the inverse function. And when you do, the result is the original x. So you got an x, you run it through f, you run the result through the inverse, and you get back the original x. The same thing happens with f of x on the outside and the inverse on the inside. So you've got an x, you run it through the inverse, you run the result through f, and you get back the original x equals x. You get back the original x. Now, they're saying that exponential functions and logarithmic functions are like that. They are inverse functions. And so, you know, maybe you've got exponential function, and it's 2 to the x. And so you've got, say, 2 to the x. Well, that's going to have an output, and we're going to take that output, whatever it is. You know, if x is 1, then the output's 2. If x is 2, then the output's 4. If x is 3, the output is 8. Whatever it is, and we're going to run it through another function, which is the inverse of the exponential function. Now, it's not going to be a big news flash that, you know, we're going to abbreviate a logarithmic function, which the idea here is that the logarithmic function is going to be the inverse of the exponential function. And this 2 here, which is the base, is also going to be the base of the logarithmic function, whatever it means. We haven't even defined it yet, but you take an x, you run it through the exponential function 2 to the x, you have an output. Well, if you run that through the inverse function, which is the logarithmic function, and it has this subscript of 2, which has a meaning, and that 2 is the same 2 as the 2 which is the base of the exponential expression, the output will be the original x. So that's a sense of what's coming with this idea of
we wish to
inverse
define
functions
an inverse
of a logarithmic and exponential functions. Before we do so, it is necessary to discuss the topic of one-to-one functions. Okay, so here's this whole other idea, but you actually do need it. You'll have to trust us. You actually do need it in order to understand the idea of inverse. Only certain functions are one-to-one or have inverses. A function f is said to be one-to-one if each range value corresponds to exactly one domain value. Now that reminds us of a definition, doesn't it? We've seen something like that before. The words exactly one were very important, and that definition had rhythm like this and some of the same words. And that definition was the definition of function itself. This is the graph of a one-to-one function. Notice that if we choose two different x values, the corresponding y values are different. So if x is 0, then y is 1. And if x is 1, then y is about 2.8. That sounds familiar. Now, we can see that this thing is a function. It passes the vertical line test. If you draw any vertical line, and we see two of them on this grid, if you draw any vertical line, it's only going to have one point of intersection with the graph. And so it is a function, but we're claiming something more for this particular one, that it's going to be one-to-one. Now choose any other pair of x values. Do you see that the corresponding y values will always be different? We couldn't pick another x value which has a y value that it would be the same as one of the y values that we've seen up to now, right? Pick, say, this x value right here, and you're going to get a y value which looks like it's about 1.8. It's different than the 1 and it's different than the 2.8. So it is true that the corresponding y values will always be different for different x values. Well, there's also a horizontal line test. We just mentioned the vertical line test, and that of course is the test to see whether the graph you're looking at is the graph of a function. There's also a horizontal line test. For the graph of a function, its graph must pass the vertical line test. That is, a vertical line will intersect the graph only once at each x value. There's a similar geometric test to determine if a function is one-to-one. It is called the horizontal line test, and it works exactly the same way. It works exactly the same way. So the vertical line test is a test for being a function. The horizontal line test is a test for being one-to-one. Any horizontal line drawn through the graph of a one-to-one function will cross the graph only once. If a horizontal line crosses a graph more than once, then the function that is graphed is not one-to-one. And of course we have seen, a lot of those. For example, the squaring function is not a one-to-one function, right? If you have y equals x squared, it's going to fail the horizontal line test. Passes the vertical line test, it is the graph of a function, but it's going to fail the horizontal line test. It is not one-to-one. Which functions are one-to-one? Well, you look at it and you say, well, does the thing pass the horizontal line test? Well, we've already kind of spilled the beans on this one, right? That one is out as a one-to-one function. But the other one does pass the horizontal line test no matter where you draw a horizontal line, it has exactly one point of intersection with the graph. Only one point of intersection, be it there, or there, or there, or there, or there, and that would happen no matter where we drew the horizontal line test. So this one is 1 to 1. 1 to 1. The other one is not 1 to 1. If f is a 1-to-1 function, then the inverse of f is the function formed by interchanging the independent and dependent variable for f. So here is your definition of the inverse function. Okay, it's a very good definition. Basically what it's saying is you're going to switch x and y. Independent variable is x, dependent variable is y. You're going to switch x and y, and when you do that, you get the inverse. Now, this also works for individual points on the graph of a function. If a point AB is a point on the graph of f, then BA is a point on the graph of the inverse of f. So here's let's take a 1-to-1 function, maybe the square rooting function. The square rooting function happens to be 1 to 1. Y equals the square root of x. It's a 1-to-1 function. You can kind of see how it would pass the horizontal line test. Well, what's a point on the graph of this function? Well, it's the point 4. One point is the point 42. That means that whatever the graph of the inverse of this square rooting function is, that inverse is going to have the point 24. Okay, so we're going to look at another example in the next video of inverse functions, and that will be the exponential and logarithmic functions. If a function is not 1-to-1, fails a horizontal line test, then the function will not have an inverse. So that is the significance of not being 1-to-1. You will not have an inverse. If you are 1-to-1, then you do have an inverse. That is why 1-to-1, just as a parenthetical note over here, 1-to-1 sometimes is called being invertible. Invertible. That's kind of a more helpful word for it because it tells you, oh, this thing has an inverse.